In the previous lecture, we introduced the linear correlation coefficient, which is a numerical measure of the strength and direction of the linear relationship between two variables. We're going to expand on that discussion by introducing the hypothesis test procedure for a linear correlation coefficient. If a claim has been made that there's a linear relationship between two variables for an entire population, one way to test that claim would be to follow our 6-step procedure. We're also going to do some examples of making predictions for the value of one variable based on the value of the other variable in the case where we conclude that there is a linear relationship between the two variables. The 6-step process is the same one that we've used in the past, but some of the steps are going to seem a little bit different because we're not testing a mean or a proportion. Instead, we're testing a correlation coefficient. For example, the hypotheses are much more restricted here than they are in the other examples. When you're conducting a hypothesis test for a linear correlation coefficient, the null hypothesis will always be the claim that there is no linear relationship between the two variables. And the way we denote that symbolically is to say that the linear correlation coefficient for the population, which we denote by rho, is equal to 0. When rho is equal to 0, that's an indication of no linear correlation. We're still following the same rule we had before for the null hypothesis, which is that it must be an equation, it must be a statement of equality. But here there's a restriction. The number will always be 0. And one of the nice things about using the calculator is that the calculator won't let you select another number. You'll see it when we get to the calculator function. It requires that you compare the value of rho to 0. It doesn't give you another option. The alternative hypothesis will somehow contradict this. And we could either say that rho is not equal to 0, which means that there is a linear correlation between the two variables. You could test the claim that rho is less than 0, which means that there's a negative linear correlation. Or you could test the claim that rho is greater than 0, which is the claim that there's a positive linear correlation. In the textbook that these lectures are based on, they always use the not equal to option, and so that's what you're going to see in this video. But if you wanted to conduct a hypothesis test for a specific direction, you could do so by choosing one of the other inequalities. Step 2 is to identify the level of significance alpha. This will be done in the same way as it has in the past. You're just going to identify it in the problem. In the real world, the common value of alpha that you would use is 5%, 0.05. Step 3 is to collect the sample evidence, and here it will just be the raw data, the list of x values and the list of y values. In the video lecture, I'm always going to use L1 for the x list and L2 for the y list, but you could use other lists if you wanted to. You'll just have to adjust what you put into the calculator function. That calculator function is called LinRegTTest, and that's what we're going to use to calculate the p-value. LinReg stands for linear regression. T because we're using the t-distribution, and test because it's a hypothesis test. The steps for making the decision are the same as always. If the p-value is less than or equal to alpha, we're going to reject the null hypothesis. Remember that the null hypothesis is the claim that there is no linear correlation. So when the p-value is less than or equal to alpha, we reject that claim and we're going to conclude that there is a linear correlation between the two variables. If the p-value is greater than alpha, then we can't reject the null hypothesis, and therefore we cannot support the claim of a linear correlation between the two variables. So in step 6, if we reject the null hypothesis, we're going to say that there is a linear correlation between the two variables, and if we fail to reject the null hypothesis, we'll say that we couldn't show that there was a linear correlation. There's not enough evidence to conclude that there's a linear relationship between these two variables. Now, as we look at our first example, you'll immediately notice that these problems look different, and it's because we've got two lists of data. When you're calculating a correlation coefficient, you need to have the paired values of the two variables, and so we've always got these two lists of data. It makes the problems kind of stand out. Let's read through this one. Below are the birth lengths in centimeters and the adult heights in centimeters of 10 males. So in the first row, you see how long these people were when they were born. And in the second row, you see how tall they were when they reached their adult height. Here's the charge of the problem. Test the claim that there is a linear correlation between the birth length and adult heights of males. Use alpha equals 0.05. Okay, let's go through our 6-step process. Step 1, we're going to determine the hypotheses. In this procedure, the null hypothesis is always the claim that rho is equal to 0, which is equivalent to saying that there is no linear relationship between these two variables, that there's no linear model that would link the birth length to the adult height of a male. The alternative hypothesis is going to contradict that in some way, and if you look back, you'll notice it doesn't specify a direction. It just says a linear correlation. So when you're testing for a linear correlation without specifying a direction, you're going to use the not equal to symbol. Step 2 is to identify the level of significance, which we denote by alpha. It's 5%, 0.05. Step 3 is to collect the sample evidence, but the sample evidence is just the raw data that was given to us. The x variable we're going to put into list 1, and the y variable we're going to put into list 2. For this first example, I'm going to remind you how to do that. In every example after this, I'm going to cut the part where you watch me typing the numbers into the calculator because I don't think you really want to watch that. But here's a quick reminder of how to put the data into lists. Press your stat key, choice number 1. You might have some numbers in your list. To clear that out, you scroll up to the list name, push the clear key and the down arrow. You would do the same thing for list 2. Scroll up to the list name, push the clear key and the down arrow. We're going to type the birth lengths into L1 and we're going to type the adult heights into L2. So the first birth length is 47, the second is 53, and so on. Use your right arrow to scroll over to L2 and we'll type in the adult heights. You can see the first one here is 168, the second is 181, then 175, 178, 183, 178, 186, 174, 177, and 170. Now we're going to quit back to the main screen with second and the mode key. And we used this calculator function in the last video, but I ran through it really quickly. Let me go a little bit slower here. Press your stat key, scroll to tests, and we want LinRegTTest, which in my calculator is choice F. In some calculators it's choice E. But make sure you find LinRegTTest. There's also a LinRegTint that we're never going to use. So make sure you pick the hypothesis test. Hop inside. Because I put my x variable in L1, I want xlist to say L1, and because I put my y variable in L2, I want my y variable to say L2. Ylist should be L2. If yours doesn't say that, you push second and the number of the list. So if I wanted to type in L1, I'd push second and the 1 key. You can see that there's an L1 right above it in the same color as my second key. And if I needed to change ylist to L2, I'd push second and the 2 key. You're going to leave frequency at 1 for every example that we do because we're not using frequency tables, we're using the list of raw data. So always leave that at 1. The next line allows us to pick the direction of the inequality, and we're always going to use the not equal to in this video, but if we were testing for a negative linear correlation, we'd choose the less than symbol, and if we were testing for a positive linear correlation, we'd choose the greater than symbol. Notice that the calculator doesn't let you pick a number for the hypothesis. It requires that you use 0, and that's good because that's the number that we always use. There's no option there. You'll also see a beta sitting here and the ampersand. You can ignore those. We're only doing the linear correlation part of this test. As such, you can skip over typing in any kind of regression equation and just go to the calculate command. We're going to get a ton of information, but for the hypothesis test, focus on the p-value. The p-value here is very, very small. I know it looks like it's 2 point something, but notice it's in scientific notation. So it's actually around 0.000002. We get a very small p-value here, and that indicates that the value of r has a large magnitude. It's either really close to +1 or -1. You can actually see the value of r if you scroll all the way to the bottom. And you can see that r is almost 1. We have a very strong positive linear correlation in the sample, and the p-value is basically telling us that the strength of that correlation in the sample allows us to conclude that the population is also probably going to be linearly correlated. Our p-value is definitely less than alpha, so we're going to reject the null hypothesis. And remember that the null hypothesis was the claim that there's no linear correlation. We are rejecting that claim. We're saying that the claim that there's no linear correlation between these two variables is false. If the claim that there's no linear correlation is false, then the claim that there is a linear correlation must be true, and that's what we're going to conclude. There is enough evidence to support the claim that there is a linear correlation, you could also say a linear relationship, between, well, what were our two variables? The birth length and the adult heights of what population? Well, this was of males. Let's go through our conclusion one more time. We're saying there is enough evidence to support the claim because we've rejected the null hypothesis. We're pretty sure the null hypothesis is false because we have a lot of evidence indicating as such. The p-value is very, very small. Since we've rejected the null hypothesis, we're supporting the alternative hypothesis. And what does the alternative hypothesis say? Well, the claim that rho is not equal to 0 is equivalent to the claim of a linear correlation between the two variables. So we are going to support the claim that there is a linear correlation between the two variables. And what were the two variables? The birth length and the adult height. Of what population? Of males. So we're pretty sure that there's a linear relationship between these two variables. Now, when we conclude this, it means that we could use the linear model, what we call the regression equation, in order to make predictions for the value of one variable based on the value of the other variable. So we're going to do this extra step. First, we're going to find the regression equation, and then we're going to use that model to make a prediction. In this case, use the model to predict the adult height of a male who was 52 centimeters long at birth. We can get that model from the calculator. You'll have to scroll around a little bit, but you can find the values of A and B in your calculator. And remember that the calculator uses a model that's a little bit weird to those of you that have just come out of algebra. It uses the model y equals a plus bx instead of the more common y equals mx plus b. So A is around 59 and B is around 2.3. So our model is y equals 59 plus 2.3x. So how would we use this model to predict the adult height of a male who was 52 centimeters long at birth? Well, remember that the birth length was the x variable and the adult height is the y variable. So we're just going to plug 52 in for x and then do the arithmetic to get the value of y. So y equals 59 plus 2.3 times 52. And then we just bang out that arithmetic. I'll do that with a calculator. 59 plus 2.3 times 52. The predicted height is around 178.6 centimeters. Aside from making predictions for specific values of the variable, we can also interpret the equation of the line in certain ways. For instance, the slope here has an important meaning. Basically, the slope says that a 1 centimeter increase in the birth length corresponds to 2.3 centimeter increase in adult height. So the model predicts that if one child is 1 centimeter longer than another at birth, then when they reach adult height, that child will be 2.3 centimeters taller. Now, of course, that doesn't have to be true for every individual. This is just a prediction, or sometimes we use this to represent an average. On the average, a 1 centimeter difference in birth length corresponds to a 2.3 centimeter difference in adult height. We can also think of this calculation in the bottom the same way. Rather than thinking of this as the prediction for an individual, we might think of this as a prediction for the average height of all males who were 52 centimeters long at birth. We're not claiming that this is equal to the population mean height of all such people. This is a prediction for that average. A study is done to see if there is a relationship between the time a patient waits to receive care and their perceived quality of care. The table below pairs the waiting times in minutes with the perceived quality of care on a scale from 1 to 10 for 8 randomly selected patients. So you can see on the top we have the list of data for how long each patient waited, and below the score that they gave from 1 to 10. Test the claim that there is a linear correlation between waiting time and perceived quality of care. Use alpha equals 0.05. Let's go through our process. Step 1, hypotheses. The null hypothesis will always be the claim that rho is equal to 0. When testing for a linear correlation between two variables, the null hypothesis is the claim that there's no linear correlation. The alternative hypothesis will be the claim that there is a linear correlation, and since it doesn't specify a direction, we'll use the not equal to symbol. Alpha has been set to 5% again, 0.05. The evidence is the raw data, and we're just going to put that into the calculator. I'm not going to make you watch me type the whole list this time, but I do want to remind you how to clear your lists. If you press Stat, Choice 1 to edit, scroll up to the list name, push the clear key and the down arrow. Scroll up to the list name, push the clear key and the down arrow. Let me minimize this so that you can see the screen. Pause the video here and type in the data. When you unpause, we'll be ready to go. Okay, I've got the numbers typed in. The first person had to wait for 53 minutes and gave a score of 6. The second person waited for 24 minutes and gave a score of 9, and so on. Now we're going to run the calculator function, so quit back to the main screen with second and the mode key. Stat, scroll to tests, and you want choice F in the newer calculators. It might be choice E if you have an older calculator. LinRegTTest. If you've already changed these to L1 and L2 and you're using L1 and L2 again, you shouldn't have to modify those. Frequency always stays at 1. You shouldn't have to modify that. We used the not equal to symbol last time. You don't have to change that. Regression equation stays blank. You can just scroll straight down to calculate and hit enter. For the hypothesis test portion of this problem, we want the p-value, which comes out to around 0.017. This time the p-value is a little bit bigger, but it's still smaller than alpha, so we're going to reject the null hypothesis. The null hypothesis is the claim that there is no linear correlation, and we are rejecting that claim. Therefore, we're going to conclude that there is a linear correlation between these two variables. There is enough evidence to support the claim. What was the claim? That there is a linear correlation between waiting time and perceived quality of care. So we're saying that there seems to be some sort of relationship between how long a patient waits and their perception of the medical care that they received. Furthermore, we're saying that that relationship is linear, that there's a linear model here. What is that linear model? I'll have to scroll down one to see the value of B. You'll notice that B this time is negative. And if we scroll down to the bottom, you'll notice that R is negative too. R was around negative 0.8. The equation that we get has an A value of 10 and a B value of around negative 0.76. Y equals 10 minus 0.076x. Now we can use that model to make a prediction. In this example, we're going to make a prediction for the perceived quality of care for a patient who had to wait for 45 minutes. Remember that the waiting time was the X variable and the care score was the Y variable. So we're going to plug 45 in for X. And again, play it safe. I'm going to put that into the calculator. 10 minus 0.076 times 45. So we get a predicted score of around 6.58. Now, most likely, a person who had to wait 45 minutes would not give a score of 6.58. But this is guessing that they would either give something around a 6 or a 7, just based on their waiting time. Here it might be better to think of this as an average. The average perception of care for a person who waits 45 minutes will be around 6.58. Let's look at another example. 9 users of a certain chess website are selected at random. The table below pairs their ages with their Blitz chess rating. So at the top you see the user's ages. At the bottom you see their Blitz rating. Blitz is just a kind of speed chess. Does this data provide enough evidence to support the claim that there's a linear correlation between a chess player's age and their online Blitz chess rating? Use alpha equals 0.05. At first glance, this might seem like a decent thing to guess, that there's some sort of relationship between how old a player is and how good they'll be at chess. We're going to test that claim. Step 1 of our hypothesis test is to find the hypotheses. The null hypothesis will be the claim that there's no linear correlation. The alternative hypothesis will be the claim that there is a linear correlation. They didn't specify positive or negative, so we're going to use the not equal to symbol. Step 2 is to identify alpha, 5%. Step 3 is to collect the raw data, so we're going to type this data into the calculator. I won't make you watch me do that. So I have all my data typed in here. The first person was 41 years old and had a Blitz rating of 1205, and so on and so forth. We're going to quit back to the main screen with second and the mode key. Stat, scroll to tests. We want LinRegTTest. Again, no change is needed here. We can just scroll down to calculate. Enter. Here we get a p-value of around 0.41. That's a really large p-value. And when the p-value is larger than alpha, we cannot reject the null hypothesis. If we can't reject the null hypothesis, it means the claim that there's no linear correlation is plausible. And therefore, we cannot support the claim that there is a linear correlation between these two variables. There is not enough evidence to support the claim. And what was the claim? That there's a linear correlation between a chess player's age and their online blitz chess rating. We cannot support this claim based on the evidence that we have. Because we weren't able to support the claim of a linear relationship here, that means that the linear model probably isn't reliable for making predictions. The calculator still supplies a model. It gives the equation of the line of best fit. But we're also saying that that line doesn't fit the data very well. Since we weren't able to conclude that a linear relationship is appropriate, we should not use this linear model to make predictions. You could plug a number into the model and make a prediction, but that prediction probably wouldn't be reliable. As such, we're not going to do the prediction part of this problem because it's probably not appropriate to do so. Instead, we'll move on to another example. Our last example is a classic example. It's been used over and over again, and I couldn't help myself. I had to demonstrate it as well. The table below pairs the air temperature in degrees Fahrenheit with the number of times a cricket chirps per minute. So I found a website where somebody actually conducted this study on their own. I can't tell you what type of cricket it was or anything like that. Apparently that has an effect. But this person noted the temperature outside and counted the number of times that a cricket chirped each minute and paired the data up. So in the first slot here, the temperature was 65 degrees outside and the cricket chirped 108 times. Does this data provide enough evidence to conclude that there is a linear correlation between the air temperature and the frequency of cricket chirps? Use alpha equals 0.05. In other words, can we come up with a linear model that relates the air temperature outside to the number of times that a cricket chirps? Is there a linear relationship? Could we use the frequency of cricket chirps to estimate the temperature outside? That's what we're looking for here. The claim is that there's a linear correlation between these two variables, so the null hypothesis will say that there's no linear correlation, and the alternative hypothesis will claim that there is. Alpha was set to 5% again. We're going to put the data into the calculator. Pause the video so you can type in the data. Now that you have the data in there, quit back to your main screen with second and the mode key. Stat. Scroll to tests. You want LinRegTTest. No changes to be made here, so we can just scroll down to calculate and hit enter. And you see again we get a teeny tiny p-value indicating that there's a strong relationship in the sample data. If I scroll down to R, you'll see that R is very, very close to 1 here. The p-value is around 0.000005. That's way smaller than any reasonable value of alpha. I don't even need to know what alpha is. We're definitely going to reject the null hypothesis here. And that means we're going to support the claim that there's a linear correlation between these two variables, which nerds like me think is interesting, that you can predict the air temperature based on how often a cricket chirps. And we've got to know what that relationship is, right? It's just too interesting not to look it up. So let's see what our model predicts. Scrolling down once so I can see the value of b, we get a model of y equals 41 plus 0.22x. We're going to use the model to predict the air temperature if you count 100 cricket chirps per minute. So we're going to plug 120 in for x. (41 plus 0.22 times 120). 67.4 degrees Fahrenheit. So our model predicts that if you hear 120 cricket chirps per minute, the air temperature will be around 67, 68 degrees, somewhere in that range. That's the last of our examples of hypothesis testing for linear correlation coefficients and making predictions. If you have any questions, let me know.